Okay, so first example. Let's look at the top half of the solid ball. X squared plus y squared plus z squared is less than or equal to 1. And we're going to integrate 16z dv over e. Okay, it's a good place to pause to try to set up the problem and then resume listening to me as I solve it for you. Okay, my solution is to first draw a picture of E so I know what I'm thinking about. So the top half of a ball looks like half of a semicircle, or half of a sphere. So something like this. And then let's draw my axes on there. So this is the sphere of radius 1. So I know that's at 1. This is also at 1. And then as I go out in the x direction, that's also 1. Here's x, here's y, here's z. I'm still graphing with right-hand rule. Yes, I'm good. Okay, so this is sort of my setup. And I look at this and I say, hey, that's a sphere. Maybe I could do this in spherical coordinates to describe the region. And so in spherical coordinates, if I want to describe that region, what I should do is first turn the x and y components of it into polar, and then change the zr components into polar. And I'm telling you, this is honestly the way that works almost every single time. So I look at that, and the region I may be integrating over, let's do a little cross shading. So I'm going to first focus on this, the maximum span of the x's and y's. At the biggest in this region, they're that bottom disk. And as you go up, everything else in the region lives above that bottom disk. So it's the base of the region. So what does that look like? I've got x, I've got y. I guess I'm going to need... I already regret everything that I just drew. Let's just erase this. Let me give myself an axis that has some negative values. So, okay. X, Y, and a little circle, a little disk. Okay, so this is that blue disk that we're drawing over there. Now, we want this to be completely shaded in. And so how are we going to express that in polar? This is just theta between 0 and 2 pi, and r going between 0 and 1. And I know it's 1 because over here in the picture, we've got these two intercepts at 1 because the function itself is coming from this sphere of volume radius 1. So, and now I imagine I am at a given angle theta. So imagine you're over here at some angle theta, and you're taking your slices kind of along here, and at some point in there, you now want to do your z direction, cylindrical coordinate wise. So then it would look like you're over here at this point, and you're going up to the top of the sphere in cylindrical coordinates. In spherical coordinates, I just need to take that intuition from cylindrical coordinates and turn it into polar. So again, let's just look at the z-r axes. And so r at smallest over here is at 0, and at biggest it's at 1. So here are my bounds for r. And the z coordinates above r are determined by this equation. And so what you can do is recall that x squared plus y squared is r squared. And so this looks the same as r squared plus z squared is less than or equal to 1. And that, I know, is a circle in the RZ plane of radius 1. Now I only want the top half, so I'm only interested in this bit here. And that's because we've restricted z to be positive. And you also notice that r is going only between 0 and 1, so actually I'm just going to restrict to this right region, because when I spin that region around the z-axis, it's going to hit that other negative r stuff. So when phi zooms around to be over here, we're going to be picking up the points that are over here if we're over here right now. And that's the idea. Okay, now this region in polar coordinates is nice and easy to express. I'll do that in yellow just to make sense. So you should always remember, though, that your polar coordinates start at phi equals 0 here and are going up to phi equals pi over 2 there. And then when you're at a given phi, you are going radially outward, and that's your rho coordinate. And so the outside of this is this curve here, which is rho equals 1 because it's a sphere. You can also get that because r squared plus z squared, we said from the previous slide, is in fact rho squared. So rho squared equals 1 is one of our bounding equations, and the other one is rho equals 0. So let's just scooch up a little bit, and we'll write our final form for this integral. So 16 over 16z dv is going to become integral. I'm going to first sub in my volume form. So my new volume form is rho squared sine phi, and I just have that memorized. D rho, d phi, d theta. And I'm going to fill them in from the outside in. So I know theta wants to go from 0 to 2 pi. I'm getting that from this expression here. Now r we're not going to actually use because we reconverted r into polar coordinates over here in the right. And so our new bounds from polar coordinates, maybe I should write over here, it looks like rho is going in between 0 and 1, and phi, I said, goes from 0 up to pi over 2. And again, I want to emphasize, phi is sweeping out from the z-axis down, like away from the z-axis, and that orientation does matter. Okay, so phi is my middle one, goes from 0 out to pi over 2, and rho, my inner one, goes from 0 to 1. And so that's all just my d volume form. So I just also need this 16z. And I'm just going to use my other coordinates, my other substitutions. So on the previous page, we remember that z, it's the polar coordinate, so it's rho times cosine phi from polar coordinates in the RZ plane. And that's it. That's our setup for the integral. Things I want to point out is this integral is awesome. It's going to be really easy because all of these are all constant bounds. So this little section of a sphere in spherical coordinates is as easy to integrate over as a rectangular region in XYZ Cartesian coordinates. And that's totally awesome. Okay, and let's just assemble this and do it. It doesn't really look all that bad. I've got a sine and a cosine, and I've got rho cubed, but all the bounds are constant, so I know no new functions are going to show up to mess around with things. So let's zoom out a little bit, and I'm just going to give myself some space to work. That looks good. Okay, so this looks to me like I'm integrating phi 0 to 2 pi, theta, phi 0 to pi over 2, and rho 0 to 1. I've got 16 rho cubed, sine phi cosine phi, d rho, d phi, d theta. Now, because the bounds are all not are all constant, you can do all of these at once or all independently. because there's no cross-talking between the variables through their bounds, through their limits. So rho cubed is going to integrate directly to, let's see, 16 rho to the fourth over 4, so rho to the fourth, and rho is being evaluated from 0 to 1. Then I've got this sine phi, cosine phi, d phi. That bit, when I integrate it, is going to give me, well, I can take u to be sine phi, and then this is really just integrating u du, because sine du is cosine phi d phi. So that's just integrating u. I get u squared over 2. So that'll be sine phi squared over 2, where phi is being evaluated from 0 to pi over 2. And I still have this remaining d phi in the equation. So just to be clear, here's my blue stuff. And the d phi is just going to give me a phi. And phi is going to be evaluated from phi equals 0 to 2 pi. So my, I guess I need maybe just a little bit more space here. Yeah, my final conclusion is that I get, from this first bit, from the rows, I get, well, rho equals 0 gives me nothing, and I get 16 over 4, that's just 4. Sine of pi over 2 is 1. Sine of 0 is 0, so I'm going to get 1 squared, which is 1 over 2 minus 0. And for phi, I get 2 pi minus 0. That's going to be 2 pi. So my final conclusion is that I get 4 pi as the value of this integral.